Well, hello. I don't know who said, hey, Kyle, but I appreciate that. All right. Hi, everybody. My name is Kyle Corbitt. I am, and we have slides. Excellent. So I am one of the co-founders of a company called OpenPipe. We do reinforcement learning for agents to make them more reliable. That's the thing that we do. We generally help larger companies, like Fortune 500 companies that have these agents. Usually what happens is they've been trying to deploy them. They can't get the reliability they need. They have a great proof of concept, but can't put it in production for that reason, and we help them get it over the line. So that's kind of a little bit of background on our company, on OpenPipe, what we do. And today I'm actually going to go like a couple layers deeper than that and talk very, very concretely about how you actually do this process. So let's say you've got one of these agents. You're trying to figure out how to actually train it, how to make it more reliable. I'll talk you through sort of the steps you go through, the steps that we go through with our customers. The project I'm going to be using as an example here is actually like fully documented. It's open source. So for those of you who are technical in the audience, I know there's some of you out there. This is like an example you can exactly follow. And at least for those of you who aren't, I think this hopefully will still be very useful to understand sort of what the steps involved are and also what the right time is to start looking in that direction. Okay, so what is reinforcement learning? I actually I caught about half of the prior presentation just as I was prepping for this one from Nathan, and I think he did a great job giving an intro, so I can go pretty fast here, but it's basically just learning from experience. It is, another way to say that is on-the-job training, right? So if you're building an agent, reinforcement learning is you're putting it in the actual environment, in the actual task it's supposed to be doing, letting it do that for a while and say, hey, you're doing a good job or a bad job. That's all it is. And concretely, as we're getting into, as we're going through this talk, there's 3 questions that hopefully you'll keep in mind, and hopefully by the time we get to an end of it, you'll have good answers, or at least have a good framework for answering these questions for your own specific tasks. And so those are, why would you want to do this? Sort of like, what is the reason you would even look in this direction? When is the right time to do this? So at what point does it make sense to sort of invest in this direction, if it ever does? And then how? So what is the, concretely, what are sort of the steps and the preparation you need to do to actually successfully pull off something like this? So why, when, and how, and again, hopefully by the end of this, we'll have good answers to those. Okay, so like I alluded to earlier, we are going to go through a very specific case study. This is a project we built internally. It's called ART-E. And it is an email agent we built that uses agentic RAG, and I'll explain what I mean by that, to answer natural language questions. So basically the idea is this is an email assistant. You connect it to your inbox, and you can ask it questions like, what time is my flight on Friday? Or what are the steps I need to do to RSVP for my daughter's field trip? Basically any question that there's information in your email. And it goes through in the background. It's going to search through your email, figure out the right keyword searches, find the relevant emails, and then come back with a natural language response that answers that question. That's kind of what it is. And we were able to achieve state-of-the-art results on this task, much better than any other model, open or closed. Okay, to make this a little bit more concrete, because I think it'll be helpful, especially for those of you who are building agents and trying to figure out what the actual steps are. This is just an example of a relatively simple run-through of this agent. And so you can see, in this example, the user's question is, what time or when is Sherry's move to Portland targeted for? And you can see the user asked that question. Then in the background, what the agent is doing is it's searching the emails. It's calling the search emails tool, and it's searching, and it's using the keywords Sherry and Portland. That makes sense. Those are probably the keywords I would search for if I were trying to answer this question myself. And setting some stuff. Then you can see, okay, the system comes back, it searches for those, and it gets back these messages from your email database. And the assistant sees that. It's like, oh, okay, we've got a couple of different results for this, and one of them looks relevant. So it's like, okay, I want to read. I think it's that. Which email is it? I'm just looking at that ID. So yeah, the first email there, it's like, okay, I want to read that email. That kind of looks like it's probably relevant to this. So then the system comes back. It's like, okay, here's the text of that email. And now our assistant is like, okay, that looks good. This looks like it answers the original question the user had. And so it calls this final tool return final answer, and it says, Sherry's move to Portland is targeted for the end of February. So this is kind of the way this agent works, the way it operates. And let's talk about how we actually built it. So the first thing we do when we're trying to build one of these is you want to get, so kind of for this step, we're leaving reinforcement learning completely aside and just saying, hey, how good of performance can I get on the task I'm trying to solve just using off the shelf? And this is what you always want to start with. Of course, you want to like just prompt and build a framework or use some agentic framework. There's lots of them out there, and see how good you can get without doing any training at all. And so this is the process we went through for this. You can see we're comparing several different models here. We've got this open source model, Qwen 2.5. It's doing pretty poorly. It's sort of the low end. It's only able to 40. So what this, by the way, what this metric means is we had this set of example questions that we gave to each of these models, in our agentic framework, and then measured the fraction of time it was actually able to correctly answer the question. That's what we're measuring here. So Qwen 2.514b could only answer the question 40% of the time. And then we can see GPT 4.171 all the way up to our maximum performing model is O3, which is the flagship model right now from OpenAI, and it was able to get the right answer 90% of the time, which is pretty good. So this is where we started from. This was our baseline, and then we went and applied reinforcement learning, and when we did that, we took Qwen 2.514b, because that's an open source model, and we applied reinforcement learning, and we were actually able to significantly exceed not just its original performance, but the performance of all of these alternative models as well. And so this 96% result is actually, the 6% difference is sort of understating the difference. Another way to think about this is, if there's 10 questions that O3 got wrong, our model after this training process was able to get 6 of them right. So it's like a 60% decrease in the failure rate. This actually, I'm going to be very honest, this exceeded my expectations going into this project. I was really happy with this result. So we're going to talk, of course, how we actually did that. Some of the benefits, besides just that increase in accuracy, this 14 billion parameter Qwen model, it's actually like a pretty small model, relatively undersized compared to all of these other ones. And there's a couple other really great advantages you get from going with a small model like that, which is the cost. It's just way cheaper to run this than any of those others, just because a combination of it's a smaller model, and also there's just a more competitive inference landscape for the open models than the closed ones. And also lower latency, mostly again because it's a much smaller model, and so it can get the responses back much quicker. So not just are we getting higher accuracy, but we're getting much lower costs per run, and also much lower latency, which leads to a much better user experience. If you're someone using this assistant, you're going to feel much happier if you get like your answer back in 1 second versus if it takes 5 seconds. Okay, so now we're going to talk about, so those are all that, this is kind of like selling it, right? Like, okay, this is why it wins. Is this actually practical? Like, is this something that you should be investing in, and when is the right time to be investing in this? And I think the answer to that, actually the answer to this is changing over time. I gave a very different version of this presentation a year ago and basically said, hey, probably not the right time right now. It takes a lot of expertise. It takes, the frontier models are advancing fast enough that you're probably not going to get your juice. I think the answer to that is actually changing over time, and I'm becoming more optimistic that this makes sense for a larger set of people. For this specific run, it cost us $80 in GPU time to do that training, which is obviously would be recouped pretty quickly if you were actually using this in production, and about 1 week of engineering time. Now, admittedly, this was 1 week of engineering time of someone who was very, very experienced in this area, so that doesn't necessarily replicate outside of that. However, I actually am pretty optimistic that a lot of the techniques that we're applying here are going to get productionized and sort of become much more sort of like turn the crank. And so I think that this is going to be something that becomes more accessible over time and is already fairly accessible, frankly. Okay, and we're going to take the next 15 minutes to talk about how to do it. Okay, so I alluded to this earlier. First step, the first rule of fine-tuning or reinforcement learning your model is don't fine-tune your model. Like, that's always where you want to start. Like I mentioned earlier, start with trying to get it as good performance as you can through prompting. A couple of reasons for that. One is you might just get good enough performance, and then you don't have to deal with any of this other stuff, and that's great. That's a great place to be. The second reason is through that process, you'll likely find, especially if this is sort of like a new agent you're building, that you were missing something. You probably forgot to give it some tool, or one of the tools you gave it was broken, or there's something wrong with your environment, and it's much easier and faster to iterate on fixing those kind of bugs if you're not also trying to iterate on training a model at the same time. So you want to get all that out of the system as much as you can, and only after that move on to reinforcement learning if you need to. Okay, so yeah, and this is just the graph we saw before. We do that. Okay, so at what point would you say, okay, now I do want to adopt reinforcement learning on my specific task? And it's basically if you're running into hard constraints on one of either cost or latency or reliability that is preventing you from scaling and from getting to the next level. If you've done everything you can on the prompting, designing your environment, giving it the right tools, and you can't get further, that's the moment when you would bring in training and you can get to the next level. Okay, so you've got now this problem. You're like, hey, I can't solve this problem through training. I want to use reinforcement learning. Great. Now you have two problems. You have the original problem you had, and you also have to figure out reinforcement learning. But also there's two problems within reinforcement learning. These are the two hard problems I'm going to go through that you have to solve if you want to adopt reinforcement learning. And I'll give examples on this task of how we solve both of them. And the two big problems you have when you're doing reinforcement learning, the first one is you want to build a realistic environment. Okay, and what do we mean by an environment? Basically, this means the area where your agent is going to be operating. So this means, what are the actual tools that this agent is going to have access to? What are the actual, types of typical responses that those tools will give as the agent's going off and doing it? This has to be realistic for the agent to be able to work well. And the second one is a reward function. Reward function is just a fancy way of saying, figuring out if the agent did a good or a bad job. And I'm going to go into more detail on both of those. Okay, so first one, realistic environment. Like I was saying, this is basically like the set of tools you give it, and not just the set of tools it has, but also like, when it calls, in our email agent case, it's like we have this tool which is search email inbox, right? And it can put in keywords and some different filters. But if the responses it's getting during training time when it calls that tool are just unrealistic, they're not like actual emails that would typically show up in an inbox, it may not actually learn the right behaviors that will transfer to real usage with real users. So you got to figure out how to get that. How do we do that in this case? So basically, for this email agent problem, we had to figure out how do we get a realistic email inbox. It should have very diverse emails. It should have, lots of things that would realistically be talked about. And it should have lots of them. A lot of us have email inboxes with tens or more thousands of emails in them. And so we wanted to have that be as realistic as possible. It's like, okay, well, where do you find that? You can't just go ask people to give you like their whole personal email to train on. So we're very grateful to Enron for this. Enron was a energy company, sort of financialized energy company in the early, the 90s and 2000s, which very famously ended up getting completely shut down for fraud. So yeah, don't do fraud, but we're very grateful they did, because as part of this as part of the trial, they ended up, as part of the discovery process, releasing 500,000 emails from executives internally at Enron. And so we were able to use that as a realistic environment of these are realistic emails. And so we were able to build different inboxes from that data set that was released as part of that discovery process when they were shut down. Okay, so that's the first problem. We now have realistic inboxes. We had 30 different inboxes from this data set that all had thousands and tens of thousands of emails in them. Okay, the second problem, the big problem you have to solve if you're going to be training an agent, is you need a reward function. All right, what is a reward function? So Nathan talked about some of this earlier with reward hacking, but basically a reward function is how you decide if the agent did a good job or not. So after it's gone through, it searched your emails, you have to be able to say, did it succeed, did it fail? Okay, the right way to do this is unfortunately very problem specific, but I'm going to give you an example of how we did it here. And the way we did it here is by actually coming up with synthetic data where we gave chunks of email to our an agent. I think we used Gemini 2.5 Pro for this part, and basically said hey, here's 20 emails, and then here is a question, and then we asked, given these 20 emails, write realistic questions that a user who is searching their inbox might have that this specific email or one of the emails in this set answers, and then also give us what the correct answer would be in that case. Okay, so that's what we did. We got several thousand of these. And we went through a process, I'll link to a blog post we have at the end, but basically we went through a process of filtering those down to very realistic questions. And once we had this sort of validated set of questions and answers, then our reward function was very simple. It was actually just like, hey, we're going to give one of these questions that we have, that we generated to our agent, and then we're going to ask it, without giving it the answer, without telling it what the right answer is, to go and search our email inbox and all this stuff and find some answer and give it back to us. And then once it gives us the answer back, we used like a very, very cheap LLM model to compare the two answers and say, hey, are these answers the same or not? And if they were, it got a high reward. If they weren't, it got a low reward. OK, so basically, once that part's done, those are the two hard things, right? You just have to have the right environment. You have to have the right reward function. Once you have those, the rest of this is actually like pretty easy, pretty mechanical. And it's basically you just are going in a loop over and over and over and over again. You're having your agent go and try, in our case, to search the email, come up with an answer, give the answer back, and then you say, hey, did you do a good job? Did you do a bad job? You do that over and over and over and over thousands of times, and eventually the agent, through this process, learns what good and bad looks like. You just, you just keep doing it until it solves the problem, and this actually works pretty well. This is sort of what our metrics look like as we were tracking for this specific run. So you can see for our Qwen 2.5.14b, we started at that about 40% at the beginning, and then it sort of immediately quickly figured out some basic stuff it was getting wrong. It was able to get up to like 65% almost immediately, and then after a while, it slowly kept improving over sort of hundreds of iterations, trying this over and over again, until it was eventually doing better than not just the bad models, but every other model we compared it against. OK, so those are the basics. That's kind of how you do this. A couple of extra bonuses that might be fun, especially for those of you who are looking to do this yourself. One really nice thing about reinforcement learning is that you can throw extra stuff into your reward function. So the main reward we gave was like, hey, did it give the right answer or not? But we threw in a bunch of extra rewards, and one of them was, you might remember early on I had that latency graph where I showed our model would get the answer back about 5 times faster than O3. Most of that was just because it's a smaller model that goes faster, but part of the reason it's faster was also because we threw in a little bit of an extra reward, which was we said, hey, the most important thing is getting the right answer. However, if 2 different sort of runs of this agent both got the right answer, give a little bit of extra credit to the one that was able to get the right answer with fewer back and forths to our email, right? And so you can see the agent, because of that, sort of learned early on it was only doing like a few back and forths. Then you can see, OK, so at first it didn't really know the right search term. So you can see it sort of jumps up. It's like it's going back and forth, say, 6 times. But then as it kind of like got its feet steady, it was like, OK, I sort of get how the system works. I know how to choose the right keywords and everything. You can see over time it was using that little extra reward to go lower and lower and lower. So by the end, not only were we getting the right answer more often than the prompted models, but we were doing it going back and forth, running fewer searches against our inbox, which made things go a lot faster. That's one of the things you can do. One other thing to address is, Nathan in the previous talk was talking about reward hacking. This is a real thing. This can happen. You have to be really careful. The main way you deal with reward hacking, in my experience, is you have to actually, like every once in a while during the training process, you have to actually look at, physically, not just these graphs I'm showing now, but like actually, what did the agent do? Read the trace, read the back and forth, and say, OK, does this result look realistic? Or did it figure out some way to kind of like hack and get a high reward without doing it? So this is an example. One thing we learned in an earlier training run as we were testing this is the model quickly learned to always give some answer, right? Even if it was unconfident and didn't know it was right, it was like, well, I might as well answer something because there was no penalty for doing that. So it started hallucinating a lot. I mean, you can see even in this run, even though we had the penalty here, you could see in early runs, like 12% of the time, it was just like, it was giving an answer, but the answer was incorrect. It was not based on an actual email. So what we did is we added an extra reward, or kind of like an extra penalty, you could say, where if it attempted an answer that was wrong, that was actually a much lower score than if it just returned and said, hey, I don't know. And so this is basically something we learned from looking at those traces and saying, OK, we can see that it's always returning an answer. That's not actually a desirable behavior. We want it to also be calibrated, and if it doesn't know the right answer, do that. So this was something we were able to learn in that way. And you can see that in the end, it was returning hallucinated answers much less often than any of the comparison models. Okay, so just sort of finishing up here, kind of going back to the beginning, you often find, I'm sure all of you who are building, if you're building a tool that uses these models, you'll often find these trade-offs between capability, latency, and cost. Now, by applying reinforcement learning, we're able to expand the envelope here. It gives us the ability to have a different set of trade-offs, a better set of trade-offs on those dimensions. And yeah, tying that back to the beginning, we sort of see that in this specific example where on our example, this ART-E project, we were able to get all of lower latency, lower cost, and higher capabilities, higher reliability through this reinforcement learning. So if those are one of the things you're running into, you don't have another way of solving it, this may be a tool that you can use. Okay, so basically that's where we're at. Hopefully that helped answer some of these questions I posed at the beginning. Why you would care, why you'd want to do reinforcement learning, when the right time is, which is when you're facing one of those problems you can't solve another way, and then how we talked about the specific steps you go through. I'll be around afterwards. I'm happy to answer questions. I'm wearing a bright orange shirt intentionally, so hopefully I'm easy to find out there. We also have a booth area I'll hopefully be hanging out at. And yeah, very happy to chat with any of you afterwards if this is something you're interested in. And yeah, thanks all of you for your attention.
As